Hi, welcome. Hopefully the exam went well. So, some sort of. Okay. So we're moving into some new topics. So we are going to be moving into AC signals and looking at AC signals and how to get information from some circuits about the AC portion of it. So up to now, we've just talked about DC. So we've looked at DC sources, DC voltage sources, DC current sources. So now we want to move into this frequency. So there's some concepts we'll need to understand, and then we're going to talk about what's called a Bode plot, which is a graph that will give us information about the frequency ability of circuits. So there was the World Trade Center, unfortunately, tragic situation. There was these rescue robots that they used, and in the debris that they had there, it was very dangerous for one, and then hard to see in another. And so they would send in these robots, and this was actually in a research stage at Professor Murphy, and she had been building these. And so she built these to send in, and they were using this to try to find people and also understand if it was safe for others to go in there or not. So one thing about this, though, is with all of the debris that was around it, communicating to the robot was a difficulty. And so a specific frequency was needed to actually communicate with this robot and send and receive information. And so thinking back also with the swarm of the robobees, when you think about like a whole swarm of communication, a bee, it's really interesting. They send out a signal from the other bee to the other one, and they can actually communicate so they can travel as a whole swarm together. And so this communication between each one is done at specific frequencies. And so, as I said, we need to understand the frequencies, and then, so part of that is to understand what this first thing is, which is called a Bode plot. Some more communications that also work on specific frequencies is, as I was saying before, like when you have an internal device. Maybe I didn't say it in this class, but if I did, I apologize if it's twice. But inside you have like low signals, and so you need to not just amplify, but you need to kind of communicate. So there's different types of signals, and the way of moving them is at a specific frequency. So there's this electromagnetic spectrum where you have specific frequencies. So the wavelength, so radio is kind of in the lower one, and then you're going to see it as a higher frequency. You see a lot more signals that go through. Remember, frequency is a cycle per second if you're thinking about hertz. So it's how many of these periods are in 1 second. And so this is kind of the range of those different types of frequencies, all the way up to the gamma rays, which are the highest frequency portion of that. So the United States has a frequency allocation band. So these are hard to read, but okay, for specific frequencies, so at 0 kilohertz, it's actually not allowed to send anything at 0 kilohertz. And then 300 kilohertz, you have, it's hard to read these, but there's like a maritime mobile. So there's like very specific frequency ranges that you can use for very specific applications. So when we're on our cell phones, 30 megahertz, you are actually, okay, this one you can kind of read. So for television, it actually has this band in here. This big blue band is for broadcasting television. So when you actually are watching TV, it's being sent to you on a very specific channel, if you're not streaming, I guess. So all of these are very specific applications. There's a radio one for broadcasting. And when you tune your radio in your car, you see that you're flipping through all of the frequencies. So hopefully you guys kind of understand that there's very specific frequencies for different applications.
Is it not allowed to broadcast at 0 gigahertz or kilohertz, or is it just not possible?
It's just not possible. So those are applications where they don't actually have a, so for the maritime mobile, it actually is an encoded signal on there. And so it's more like an encryption. Yes.
Isn't it also illegal to use some of the frequencies because of the FAA?
Yeah, so this is why you have these very specific locations that you can transmit. If you don't, you can cause harm for specific things. And also like medical devices, especially if you think about medical devices, you don't want somebody to be sending something that's going to interfere with like a heart pacemaker. So there's safety involved, and that's why it is regulated by the government. And they do specify like, yes, if you want to transmit something wirelessly, you need to make sure you're in a specific frequency range. So yes, it is illegal to not be in the right ranges. So these are some of the different ones for what's called the ISM band for the industrial, scientific, and medical bands. And so these are going to be like, yes, these are okay to use for those specific applications. So there's quite a few, and usually they're, again, like they're going to depend on the application as far as which bands you would want to use. All right, any questions about this so far? Okay, so the goals of today is to understand the characteristics of a sinusoid. So we're moving into the AC portion. So we want to go back and kind of remember a little bit about sinusoids and how to look at them and get some information just from a signal itself. And then we're going to talk about the decibel and conversions between what's called a decibel and volts per volt. And then we want to find a transfer function of a given circuit and then write the transfer function in standard form. Get some information from the transfer function, which is called a zero or pole. And then we want to start learning how to draw these straight line approximation Bode plots. And then with that, we're going to talk about filter transfer functions too. All right, so that's what we're going to do today. So first thing is the signal characteristics. So here's a sinusoid. This is current. So we have what's called the peak to peak. So peak to peak is definitely the amplitude from the top amplitude to the bottom amplitude. So that would be considered peak to peak. Peak would just be the height. So that would be, what is the peak to peak here? Correct. It is 8. So this is 8 volts. What if I was just to do peak?
Isn't that 8 amps?
Yeah, 8 amps. Thanks. 8 amps. And what's the peak? Thank you, 4 volts. And that would be the same as what we call our amplitude.
4 amps.
I am not. One of those days today. Thank you. You guys can keep me on task, I guess. Okay, so amplitude is equal to peak. Then we have a period, which is the time to when it repeats. So this is considered to be 1 cycle. So a period is also considered a 1 cycle. And so in this one, that would be kind of hard to see here, but if I'm picking one point, then I go and see where it's repeated, which looks to be about right there. So this would be 1 period in this example. Or the other word is 1 cycle. So you find a spot on there that's easy to identify, and then you look at when it repeats again itself, and that would be where your period is. All right, frequency, which is in hertz, is 1 over that time period, and period is usually a capital T notation. And then omega, which is your angular frequency, is 2 pi f, and that one's going to be in the units of radians per second. So to describe this signal, let's see, amps. So I guess we already found amps, or A for amplitude, so this was 4 amps. Remember if I had all these. Okay, I didn't find them before. Okay. This is a little harder to read, so I don't really feel like you need to be able to look at the signal and actually write these. I just want you to understand the terms. So we're not going to go into the details of the actual calculations here. So we're going to ignore these. What you are going to want to do, though, is be able to know, okay, this is going to be, the form of it is a sine or a cosine. Amplitude is easy to see, and then, we're not going to get into the details more than that. All right, questions on signals and just the terminology themselves. Okay, so understanding peak to peak, period, amplitude, frequency is in both hertz and in radians per second. And we'll get more into the units when we get into more details. So this is just, we're not going to worry about this. Once you get the amplitude, the period, most of the time you're going to measure a period off of an oscilloscope, so you can put a marker and then you just drag it to where you're seeing the repetition happening. So that's where you're going to get a measurement of your actual period. So this can be measured on an oscilloscope. I can't write and I can't talk today, I guess. On an oscilloscope, so measure. So usually you can measure that, and then, oh, go ahead. Yeah. So usually you can measure the time period, and then from that you can find the frequency by taking 1 over f. So in this case, if your time period is 3.1 milliseconds, then your frequency is going to be 322.6 hertz. And then what was the units for omega? Thanks. So radians per second. And you're just taking 2 pi times that. And then to put that in the form of the cosine, it's going to be your amplitude 4. Cosine, and then you take your omega times t, and then if you have any shift, again, we're not going to worry about the shifts in here. And this would be your phi. So what I, again, want you to know is just the terminology and then conversion. So making sure you understand how to convert between these two. And then also knowing that you have frequency in hertz and omega in radians per second. Yes?
Where'd you get the theta from?
So theta is, it depends on your input signal. And what this is going to be is you're measuring your output versus your input. and how much distance there is between the output and the input. And so this delta t is a time between that measurement there. So it's a time measurement from input to output. So if you have a input that's like this, and then your output, do green. I can't draw very well. But this distance between the two, when their peaks are both high, would be like a delta t. So you would be measuring that usually on an oscilloscope again. And then from there, your time period is the t you just found, and then you just multiply it by 360 to get it in degrees. Did you have a question?
Yeah, so the rate of t is in radians, right? Because it's in radians per second.
Uh-huh.
And then pi is in degrees here.
Yeah.
So would you normally be mixing that with radians, or would you have to convert to make sure radians?
So usually you would put them in radians together. If you're doing them, if you're doing it by hand, you would put them in radians, find it at a specific time, and then put that on the plot. But usually you're going to use a graphing tool to help you graph that. So most of the time, the application of what you're trying to do is gather this information from a circuit. So you're going to look on an oscilloscope, make those measurements, and then calculate these values, and then if you want to reproduce them, you would put them into a tool to graph it. Okay. All right, any other questions? Okay, the other thing about signals that you need to understand is that now we can have both types of signals. So this is an AC only signal. And your DC here would be equal to 0. It's centered around 0 volts, which is easy to see because it goes above 0 the same amount as it goes below 0. So this would be said that there's no DC component of this. It only has an AC component. So every signal can have both types of signal to them. So you have every signal has a DC and an AC. So for this example, 2 volts would be considered your DC, and then the sinusoid would be your AC. So this doesn't, it looks kind of skewed here because this goes up to 6 volts here, and then down to minus 2 volts here. So it's actually centered around 4 volts. Or 2 volts would be 2. 4. 4 goes up by 2. No, it is.
Center around 2.
Thank you. Just a minute. It's got to be around 2. Okay, so your center is 2. It goes up by 4 and down by 4. There we go. And so centered around 2 volts, which is why you get that DC. So if you were to measure this on an oscilloscope, you would see that. If you changed it out to not have any DC, it would then show you the first graph and just the AC component in there. So on an oscilloscope, you have the option to see just AC or just DC or both. Sometimes your AC portion is not a sinusoid, and it can be something that's more like random noise like this. So this signal we would describe as having a DC component of 1 volt, and then it ranges because it's kind of chaotic. We don't have a periodicity to it, so it would just be a plus or minus value of that. And that's what you're going to see with noise, or if you measured if you measure the wall output, you're actually going to see a 60 hertz sine wave kind of in there along with a whole bunch of noise. So this would be your DC, and then is 1 volt, and then your AC component would be the plus or minus 1 volt. So this would be considered your AC portion. All right, question? Yes.
And so the AC is just noise, is what you were saying?
It can be just noise, yeah.
Okay, or it could be like an actual, like, wave plus noise as well?
Yeah.
Okay.
Yeah, so sometimes you may see
Oh.
something that kind of looks like that, where it does have an underlying sinusoid in it, but there's still noise on it, so it's not a clean sinusoid.
Gotcha, okay.
So this is kind of what you see when you measure, most of the time when you measure a wall output, because it has an underlying 60 hertz signal to it, and then it will have the random noise kind of in there too from other effects. All right, other questions? Any other questions? Okay, so the next thing we need to understand, so first thing is these signals. So now we're going to talk about signals as far as like specific frequencies and limitations that a circuit may have with specific frequencies. So to do that, we're going to work on being able to draw what's called the Bode plot. And to do that, you need to know a new term called the decibel. So this unit, decibel, is dB, and it is a term that Alexander Graham Bell found that our ears actually hear non-linearly. And so what he found was that he could describe actual like loudness in a log form. And so our ears actually hear in a log form. And so this is a conversion so that when we look at it, it actually looks linear on a graph. And so that's where the decibel came from. So we're going to use this decibel. And in our graphs, you're going to see it as the y-axis is in decibels, and then the x-axis is in frequency. And so to convert, we need to know how do you convert. As I said, it's a log form. So in an equation, when you solve for our equations that now have AC signals in them, you're going to get the result of a volt over volts. So it's going to be dimensionless, and bells are also dimensionless. So that's a good one. Dimensionless. No. So they're a dimensionless unit. So volts over volts is actually our output over an input. So this output over input is also called a transfer equation or transfer function. So if asked what is a transfer function, that means that you found the output equation in terms of the input, and all you do is divide the input over to the other side, so it doesn't matter what that input is, and then you have an equation on the other side. That equation is called the transfer function. So when we derive this from hand, we're going to find that value to be in volts per volt. And then to convert to dB, we take the value, multiply it by log, and then or take the log of that and then multiply it by 20. And that gives us the unit in dB. To go back from dB to volts per volt is we take our dB number, divide it by 20, and then raise 10 to that number. Okay, so if you use MATLAB, you need to use it log base 10. So it's log 10 and then the number in there. So just note that. Calculators, you'll have to figure out what your own calculator does. So we're going to just do a minute to do conversions for these. So find the dB for when you have 4 volts per volt. Find the dB for when you have 1 over 4 volts per volt. And then find volts per volt for when you have 46 dB and then when you have minus 46 dB. So take a second to try to solve for those. Yeah. So that's just the variable name for that.
Blankest stare I've ever seen in his eyes. I said, give me 5 minutes.
Wait, how am I getting a negative decimal?
That's what I'm saying. Why it doesn't have negative?
It's not. It's just. It's because
You're in quiet. Your output's quieter. So you're losing the logarithm. Just think of decimals as going.
it actually.
There's always a reference.
Absorbing sound. Then you divide by 20, so you get 2.3. 2.3. And then you would do 10 pounds.
Your decimals.
All right, so for those that put them in, great. So Any questions on these conversions? What do you notice about this?
The negative decibel.
The negative decibel means what?
It's absorbing.
So it's not absorbing, it's just meaning that it's a 1 over some number. So it's a reciprocal of a number. So from this one, if the volts per volts was around 200 and you take 1 over that and take the dB, it gives you a negative value of that dB. So it's a reciprocal version of it. Does that make sense? So this is good to know because if you see a negative decibel, it just means like, oh, I have a very small number. So if we're thinking about this as output over input is equal to this number, if we have a large number or a positive dB number, it means that our output is greater than our input. And so we're amplifying that signal. If we have a lower number, that means that our input is greater than our output, and we've done what's called attenuating or reducing our signal. So that's what those negative dBs mean too. So the signal has been reduced. So a negative means that our input signal is reduced. And a positive dB means output is amplification of the input. All right, does that make sense? Maybe, maybe not. Okay. So engineers always love to find a way to make things a little bit simpler and applicable. So instead of solving circuits in the time domain, way easier to move them into the frequency domain, get a solution, and then take an inverse back into the time domain for that end solution. So we looked at RC and RL, which are time-dependent elements. We looked at when we put DC only on them. So as an input, we only had omega was equal to 0. So we didn't look about what happens if we put a whole bunch of different frequencies on these inputs. And so that's what we're going to look at next. So, but for one element, we had one differential, remember? We had 1 d over dt. Every element that I have in a circuit would then add in another differential to that, to where I don't want to be solving a 6th order differential equation by hand for a circuit that may have like 6 of these components in them. So instead, all we have to do is change them into this frequency domain. And it's an abstract domain. It's hard to visualize what's happening there. So kind of this abstract domain, it changes all of our differentiation into a multiplication or a division. So much easier to add and subtract and multiply and divide. So that's the reason why we want to do this. And it's a way simpler way of solving the circuit. When we're in the frequency domain, then we can analyze it using all the techniques you've already learned. So you can go back to KCL, KVL. If it's a circuits or elements in parallel, you can combine them if as an impedance, or if they're in series, you just add them. Instead of having to say, like, I have 2 capacitors here, and now I have to do, anyway, make it more complicated. So any number of capacitors, any number of inductors is going to be way easier. What each of these elements does is create, though, what we call a polar zero. So it creates a frequency change. So a polar zero means that I have that many elements, time-dependent elements in my circuit. So if I have 3 time-dependent elements, that means that I'm going to have 3 either poles or zeros in my circuit. So one thing we need to know, like if we're moving from time domain into this frequency domain, how do we move our elements that we know? So a resistor is really easy. It only has a real component to it, so it just moves over as a resistor. For the capacitor, though, that has a time dependence, okay, I'm missing a C here. That should be 1 over CS. My C's got moved somewhere there. It's going to be 1 over CS. And then I treat this as both of these you're going to treat like a resistor. For the inductor, it's going to go into transforming as SL. And then we use that value and then solve the circuit. So if I have a capacitor and an inductor in series, then I just add them together. It would be 1 over CS plus SL. And then to manipulate the equations, once I get into the S domain, I use this transformation of S is equal to J omega. And then I'm going to have a complex number. So once I get this complex number, I use the rules of math of complex numbers, and then I can add, subtract, multiply, divide using the rules of complex numbers, and then I get, in the end, I get this output expression that's output is equal to some function, some numbers times my input. I take that input, I divide it to the V out, and that's my transfer function. Okay. All right, so frequency domain versus time domain. So you have in frequency, we already talked about that you have both omega, which is your frequency portion, and you have a phase portion of it, the phi. So in here, we're going to look at just the magnitude portion, which is going to be, sorry, that wasn't, magnitude is A. I really cannot talk today. So A is your magnitude, and then you have the frequency range. So each of these has omega, and this is T versus your amplitude. And so on your magnitude, if I am looking at only one frequency, which is 3 hertz in this case, I'm going to get one point on here at 2 pi f, which is going to be 3, so it's 6 pi. It's going to have an amplitude of 1 in this case, or A. And it's going to be 1 point on this graph. I only have one frequency here. Again, for the phase, it would have just one phase. This would be A. So we consider this, these are called Bode plots. And what they do is they tell us information about a signal, or they tell us information about the circuit. And so, as I showed, this only tells you information about one signal, one range, one value. But a lot of times you want to know over the whole frequency what's going on. What if I change this from 3 hertz to 1 hertz or 1 million hertz, 1 megahertz? And so what this graph does is it tells you at each frequency what is happening at your output for the magnitude. So these are kind of the same. As I said, S is equal to J omega. Sorry, I'm going back to remember what else I wanted to point out about this. No. Frequency. Okay. Yeah, that's really it. Okay. Okay, so now we're going to look at an actual circuit. So this is a simpler circuit, but it could be the same steps could be applied to that one. So to solve this, we want to get the transfer function, which is this H omega or H of S. And then we want to graph this. So what happens with the resistors when we move over into the frequency domain? They stay the same, so I don't need to do anything with this one. We're going to use a generic input, Vn, and we just know that this is a sinusoid. So we know it has frequency to it, but we're not specifying exactly which frequency it is. What do we do with the capacitor? Correct. 1 over CS. So S is this abstract frequency domain. And then so S is easier to use than J omega, but you could do this as a solution of C is J omega.
And what's J?
J is an imaginary number. So it basically means that it's a complex number. So we call these complex impedances. So C and J are called, or C and capacitors and inductors are called complex impedances. So I like to work with S, and then I'll change into J when I'm doing more algebraic manipulations. Either of them you can start off with, though. All right, so we want an equation for V out. So thinking about capacitor as a resistance here, or impedance, do we know how to find an equation for V out? Okay, good. Voltage divider. So we want the voltage across here, right, to ground. So that's going to be the voltage across the capacitor. So we just use that as this one. V out will be your V in is your source times 1 over CS. And then 1 over CS plus R. And this would be my output equation, and it's already in the function of input. So to get the transfer function, all you have to do is do a division, and there's my transfer function. This is a transfer function because I have it in terms of S. But that's basically all you have to do to get the transfer function. So to put it in terms of H of omega, you're just going to substitute in that S is equal to J omega. So it's 1 over C J omega all over 1 over C J omega plus R. So to get that Bode plot of this, which is going to give us all the information over a range of frequencies, we're going to take the magnitude of this. So now when you take the magnitude, we're going to take a step back about complex numbers. So a complex number, a plus bj, anybody remember how to take the magnitude of that. It's been forever. Yes. Correct. Does that look familiar? Okay. So there is a real plane and an imaginary plane, and hopefully I can draw them on the right versions. Real. So when you guys looked at vectors, trying to think, have you guys looked at vectors? Which math class has vectors in it? All of them? All of them have vectors. Okay. So when you think about a vector, you can describe the vector on an imaginary and real plane in two ways. One of them is in rectangular form. Which is what I wrote, A plus BJ. Or you can use the polar form. So R would be your vector magnitude, and then theta is your angle from the 0 axis of real. I'll draw it there. Goes in this direction. And then your imaginary and real portions is A and B. Does this look familiar? Forever ago? Okay. So on this portion, we're only looking at the magnitude portion. So we want to understand, the R value, the hypotenuse of that. So A squared plus B squared. So looking at that, it's easier to manipulate the equations that we have. So we get like a j omega plus number. So we have a real plus imaginary. So this is our imaginary, and this is our real portion. So to do that, it's going to be easier to multiply the top and bottom of this equation by Cj omega on top and bottom to get rid of the 1 over that number. So then this will equal,
Professor,
yeah,
above was Vn multiplied by the 1 over Cjw, right there.
uh-huh.
So how did we cancel that? How did we get that out of there for the bottom equation? Because I can see that it's in the one that's circled in pink, it's h of s. The one that's in blue is h of omega. But how can we just remove the Vn from the one that's in pink to create the h of omega?
Okay. So V out was originally Vn times this, right?
Okay.
So I can,
Oh, I see. So you just divided
I just
it over.
divided it
I
over.
see. Okay, thank you.
Does that make, so I just take it from that side and divided it over.
I see.
Okay, thanks. Okay, so multiplying both the top and the bottom, Cj omega. So that leaves you a 1 on the top. And then this will be 1 plus RCj omega. So now this looks like, okay, on the bottom portion, I can take the magnitude. Well, what's the magnitude of 1? It's just going to be 1. So the top portion would be 1. And then I could take the magnitude of the bottom portion, and that is going to be the a squared, the square root of a squared plus b squared. So when I take the magnitude, I take the magnitude of the top and the magnitude of the bottom. So this one ends up being 1. This ends up being the square root of the A portion will be 1 squared, and then the B portion of this will be the RC omega. And all of that squared. And that's going to be my magnitude. So if I want to plot this, I can put in different values of omega. So say I put omega equals 0.1. That's going to be 1 over 1 squared plus whatever r squared is, c squared, and then my omega is going to be a 0.1 squared. And that's going to give me a specific value. Yes.
Where did J go?
So,
In the magnitude of 1 plus.
uh-huh. So the magnitude of a generic form of a plus bj is going to be, so a plus bj is the rectangular form of a vector.
Okay, so that's just directionality.
Yeah.
Vector, okay.
So with that, then you take the magnitude of it, and that's just the number, which gives you that r value. So it's basically the, you're changing it from rectangular form to just know the magnitude of it. So that's why there's no j there. And that's what we want to know from the magnitude is what is that value? What is the magnitude of the vector? What is the magnitude of the signal? Does that make sense? Sort of?
I'll go along with it.
Okay. All right, any other questions? I'll go along with it. Okay, so now I can go and do a whole range of omegas. You know, omega equal 0.2, omega equal 1, omega equal 10, omega equal 1,000. So I can do a whole array of omegas, and I'm going to get an answer for each one. I can then plot this with omega is the variable, so that's why I could change it each time. And then I'm going to get a specific answer for each one of these values. Yeah,
Does that say R of omega squared or RC omega squared?
RC omega squared. RC omega squared.
And that's true for all J omegas, or what is that equivalent to?
So that's the magnitude of this transfer function.
Okay.
This is j omega.
So, what, before it was h of omega, and
Uh-huh.
now it's h of j omega, does that cause a difference?
It's the same. I'm
Okay.
just trying to think how to say it differently. But yeah, it's the same. It's you replace s with j omega.
Okay.
I think it probably looks better to have it be j omega. I'll leave j omega in there because that is more consistent.
Okay.
Okay, any other questions? Okay, so now yes.
I'm still a little confused where the C comes from in essence. I'm just a little confused on the magnitude of the C person.
Magnitude
In
is,
the magnitude of the H of S equation we had, I understand the R omega squared, I just don't understand the, does the C come in for J? I'm just a little confused.
okay, so C and R are actual numbers, so we can go plug those in. So 100K and 0.04 micro.
No, I understand that, I'm just not sure where it came into that equation. Because I understand the magnitude, but I'm just still a little confused where.
Did you understand getting to this point?
Oh, yes, okay, yeah.
Okay, so then this is really 1 over 100K, 0.04 micro S plus 1. And then I just was leaving it in symbolic form here. But this is really 100K. Oh, it's missing a Where'd my C go? Yeah. So this should have a C in there too. RCJ omega. RCJ omega. Yeah. All right. Yeah, that was missing a C in there. Might be why you were confused. Okay. So those are actual values, and then we can plug those values in and plug a value in for omega and get a specific point for each of those omegas on here. And then we can connect them for a smooth graph. But I don't want to plug in my calculator every single omega value to make this graph, so there is an easier way. But I want you to understand, like, this is the process of getting to the easier way. So this is our graph, and as I said, when we plot it in dB, we have what is called a semi-log graph. So on the y-axis is going to be your omega, and your omega is the log portion, and the y one is a normal linear step. So here you can see minus 60, minus 40, minus 20, 0. Each of those is incrementally looks the same, going up in the y. So this side is normal. How you do a log graph is that the first division is 1 increment, and then the next one would be next. This would be 3, 4, 5, 6, 7, 8, 9 to the 10th. So with a log, it actually has a large division, and then it goes smaller as you get to the next 10th. And so from here, this first one's going to be 20, then 30, 40, 50, 60, 70, 80, 90, and then it would be 100. And then the next section's going to be 200, 300. Does that make sense? Okay. So you're going to need to verify, like, to understand where these are, so that if you're going to graph this by hand, you have to find, if you're at 500 for your omega, it's not going to be right on 100 or 1K or something else. So you need to know how to read that to be able to say, where is my point that I need to get. So we're going to find a few points on the graph, and then from there, we're going to be able to look at the equation, and I'm going to show you a technique to just draw the graph really quickly. So, other thing to note here is what's called a decade. So between 1 to 10, this span is called a decade. So a decade is a multiplication of 10. So it goes 1, 10, 100, 1K, 10K, 100K. If you're starting at 500, your decade after that's going to be what? 5,000, thank you. Decade after 5,000, 50,000. So it just keeps incrementing. If I start at 20, what's the decade after 20? 200. And the reason I'm explaining this is the way it does it by hand is that you're going to increment things by decades. So that's why we want to know what this decade is. Okay. Any questions about the semi-log graph itself? So the x-axis is the log, y-axis is a normal. Understand what decades are, and make sure you understand how the division on the log graph is made. So each division is an increment from the first unit. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the next sections go by 20s. 20, 30, 40. The next section, because it's now in the hundreds, goes by hundreds through those. And each line is an increment from whichever unit it's at. Okay, so let me grab the equation. Okay, so on this, I actually have a flat line until I reach a certain point, which looks to be about 250. And then it decreases. And so if I was to put in 2, 3, 4, 5, 6, 7, 8, 9, 10, I can get specific points for each one of these. By plugging it into that 1 over the square root of 1 squared plus my value of r squared, c squared, and then omega being 2, 3, 4, 5, 6, 7, 8, 9, 10. And I can do that for the whole graph. Then I connect it by connecting all the points, and it gives me the continuous graph that looks like this. So this is the plot of that h omega. This point here is called your critical frequency. Or you'll also see it be called a break point. So what I notice at this point is that between that point to a decade after, so where would be my decade? About 2. It's going to be about here. How far, what is the slope of that? So it goes from 0 to about minus 20. So approximately minus 20 dB over 1 decade, right? What about going one more? It's almost about the same. It looks like that slope is continuous at about a minus 20 dB per decade slope. Okay? So we can use this information, which is nice. We only had one capacitor in this. The capacitor equation ended up, grab the whole equation. Okay, so here's my H of S equation. So what I notice from this is that for one capacitor, I only have one S, and that S is in the denominator here. And when I'm in the denominator, these are called poles. So a pole will be in the denominator, and a 0 will be in the numerator. So what I notice from this is for a pole, I have the effect of once I've reached the pole value. So let's see, R was, let me calculate this out. R was 100K, and then C was 0.04 micro. And RC so 1 over RC is 250. And so if I was to solve this for a root, I would set this up, and it would solve to give me S is equal to minus 1 over RC, right? So if I solve my equation and find the roots of that equation, those end up being my poles and zeros. So these poles and zeros are the roots of the system or equation. The negative value affects your phase. And so we only look at the magnitude of the root. Okay? And then that root ends up giving us a location on our plot of that critical frequency or break frequency point. So the nice thing about this is once we locate it, what those poles and zeros are, we say, like, if it's a pole, it's going to give us the effect that it's going to go after the pole, it decreases by minus 20 dB per decade slope. So that makes it really nice because now we can just look at this equation and say we have one pole. We don't have, I'll show you the effects of the other ones when you have them at the origin. But we have one pole. It's going to be flat till I reach that pole, and then it's going to drop off by minus 20 dB per decade. I can just draw this graph right away.
So the amount of S's is kind of how many poles there are?
Poles or zeros, depending on if they're in the top or bottom.
What do you mean zeros?
A zero will be if there's like a S in the numerator. So if I had like S plus 1 up here, that would be a 0. The S up on the top would be a 0. And my value for that 0 would be 1 because it had 1 in front. Does that make sense?
Yeah.
Okay. All right, other questions? Yes.
I'm a little confused on how you set up the equation for solving for the root. Where'd you get the RCS from again? Are you allowed to just pull it from the HFS?
So RCS plus 1,
Yeah.
you set that equal to 0.
Okay.
And you just solve for that. The negative 1 goes over to the other side. That's all. So you just set your, so like if you have a polynomial, you usually have to take like the quadratic solution for that one, but then it becomes a factored form, and then you set those factored forms, each of those equal to 0 to solve for the S's.
For the both numerator and
Uh-huh.
denominator for
Yeah.
poles and for zeros.
Correct.
Okay.
Yep. So whatever functions you have. So we want to get it into a simpler form like this before we can then graph it. So this is called the standard form. So, all right, any other questions? Okay. So now we're going to talk about, like, generically, how are we going to look at these and be able to do that easily. Do note that 20 log of 10 of 0 is an undefined, so we never take like an omega at 0. We have to take omega equals 0.0000001 or 0.001 and so on. Also, we're not going to talk about the phase, but you would do the same idea that we're doing with the magnitude, is that you would take the angle of the whole equation instead, and then use the properties of finding an angle of a function that's complex. Okay. All right, so the first step is to put it into standard form. So it's easier to actually put it into this one, which is like S over the number plus 1. So each of these you can see is like S over a number plus 1. And then you might have some constants out in front of both the top and the bottom. So you'd have some constant and then S over a number plus 1. So usually I'll say try and get it into the standard form where you have kind of these quantities of S over a number plus 1. Or you want just S by itself. Then you're going to look at it and say the roots of the top is going to be my zeros. The roots of the bottom equation is going to be my poles. So poles are denominator and your zeros are your numerator. And these are going to be the roots. Then what you're going to do is you're going to find a starting value. You're going to calculate one value on the graph. And then you're going to move from left to right through the poles and zeros in order of lowest to highest. And look at the effect it has. Add on the slope change it has at each of those frequencies. And so you just add the effects until there are no more poles or zeros. So we need to look at, like, well, what if we just have the constant out in front? What effect does that have? It doesn't have an effect as far as a change in frequency as far as the minus 20 or plus 20. But it will affect the value. So all you do is take 20 log of that value that's out there in front, and that gives you a straight fixed value over every frequency. So that's basically where you're going to start, is at that value until you reach your first polar zero, and then you're going to have a change. The other effect is if I just have a zero pole at the origin, that's when S will be equal to 0. So if S is equal to 0 on the numerator, that means you have a 0 at the origin. If an S is on the bottom, it's going to be a pole at the origin. Each one of those is going to have a slope. So for a 0, you have a positive 20 dB per decade effect. So if you can find one value on that graph, you know that it has a 20 dB per decade slope through it, and that's how you're gonna calculate that one, is you find that one value. So we do have to take the square root of everything in there, as far as the equation, put omega equal to some specific omega value, find that value, and then we can put the slope through it. For a pole at the origin, you're going to have a minus 20 dB per decade slope. And then you already saw, so this is going to be a pole effect, and this is going to be a zero effect. So poles go down by minus 20 dB per decade, and a zero goes up by 20 dB per decade. Yes?
It's always gonna be 20 dB per decade?
Mm-hmm. Yep. It always will for each one you have. If you have a double polar zero, then it's going to have double the effect, and it will actually go up or down by 40 instead of 20, and so on if you have multiple poles or zeros. All right, so the effect summary is if you have a pole at the origin, you have a minus 20 dB per decade, zero at the origin, plus 20 dB per decade. Pole, it's going to be minus 20 dB per decade above that frequency that it has at its break frequency or critical frequency, and then the pole will go down. Yes?
Are we gonna go over more actual examples?
Yeah.
Okay.
Yeah, but I wanted to explain this generically, and then you guys want to go write it in your own words. Okay? So this is the whole process in my words, and now you guys want to practice this till you can look at the graph or look at the equation and then be able to just graph it right away. Okay? So these are the steps, and yes, we'll go through more examples. So going back to this example, to get this one into standard form, all you would need to do So to get this into standard form, we need to just divide that RC to get this S over a number plus 1. So note that RCS plus 1 is the same as saying RC times S over RC. Wait, no. Yeah. No. Sorry. This isn't a good example. Let me do a different one. Okay. Okay, not getting rid of it. Okay. What if I have H of S Okay, so putting this like into standard form, we need to get that S over a number plus 1. And so note that S plus 100 is the same as so note that those are the same, right? So I take the 100 and it would be S, and then plus 1 would be 100 in there. So with that, this standard form would be 100 times S over 100 plus 1. This one is going to bring the 20 out and the 40 out, and then I would have S over 20 plus 1 and S over 40 plus 1. So this would be my standard form. I take 100 divided by 20 times 40. And that ends up being 0.125. So with this, if I change this over to dB, do I expect this number to be a positive dB or a negative dB? Somebody say it louder? Negative, correct? So this is going to be my equation. I don't have any poles or zeros at the origin, so I'm going to just take 20 log base 10 of that 0.125. And that gives me kind of my starting value. So 20 log of 0.125 gives me a negative 18 dB. Let me grab the graph. So to graph this, I need to know where my other poles and zeros are. So what is my poles and zeros here? So I have a 0 at what frequency? Which one? Okay, it would be minus 100, but we only care about the 100 portion. So the negative does phase. So the root is at negative 100, but it only affects the phase for the negative portion. So we're just looking for the root value itself. So 100. So we say we have a 0 at 100. And where do we have our poles? Correct, 20 and 40. One quick note is that when I have an equation like that, my magnitude is in volts per volt unit and radians per second. So because this is in volts per volts, that's why I had to take the 0.125 and convert it into dB. Okay, so now ordering these, I have two poles, 20, 40, and then I have 1, 0. So I'm going to mark on here the 20, 40, and 1, 0. So my 20 is here, and my 40 is here, and what was the other one? And then 100. So those are my three values. I'm going to have a flat line at minus 18 dB. 18. Until I reach the first one. And then what happens at 20? It goes down by minus 20 dB per decade. At 40, it's going to go down by minus 20 dB per decade. And then it will go up at 20 dB per decade at 100. So this would go down by 20. So the next decade would be, it's going to be here. And this would be if it went the whole way. So it's going to just go until it hits 40. And then at 40, it adds another 20. So from 40 to the next decade after is going to be about, 20 to 40. It's going to go here. Yeah, it's hard to kind of draw this, but it will it will go down a little bit more, and then it's going to go not quite as steep for the rest of it. So this would be minus 20 dB per decade change. This would be minus 40 dB per decade change. And then this would be, sorry. And then at 100, sorry, this is not drawn very well, but so this is 40, and then this one at 100 would then go back to minus 20 dB per decade. So you're basically adding on each effect. These weren't great example, but we'll go through some more. That was just a very quick example. All right, so go practice trying to draw these. Yes. Correct. You can't have negative frequency, so you're just looking for the frequency itself. The which one?
Being a polar zero just tells us if the slope's decreasing or